Let us start our work today with the talk of Alexey Rudenko about Hausdorff measure of the joint trajectories of several independent Brownian motion on Carnot group. Please, Alexey.
Can you hear me?
Yes.
Yes, so everything's fine. Let me start. My talk will be about, let me show more exact description. Suppose we have independent Brownian motions on Carnot groups. I will not explain exactly what they are because I will only need them in the end, and there is no need to, because I will just use some results about them, so I don't need to specify them precisely, maybe essentially because I did it every other talk, probably. So suppose that we have such Brownian motions, and if somebody didn't hear it before, then this is just a typical Brownian motion on Carnot group. Is we take two Brownian motions, and then we take a third coordinate, which is Levy area, something like this, will work as a Brownian motion on Carnot group. Turns out that this can be viewed as a Brownian motion on Heisenberg group of three-dimensional. So in general, this Brownian motion Carnot group just some Brownian motion, standard Brownian motion plus some multiple integrals of special form. So I'm interested in a situation when I have several independent such processes, and then I look what happens with the joint trajectories, in the sense what will happen with Hausdorff dimension of this intersect with some set. Of course, this is way more general. In this talk, I will talk mostly about situations when this set is some kind of submanifold, in the sense that it is some smooth surface in this space, which can be considered as just Euclidean space. Carnot group can be considered as a Euclidean space, so it is just
But Alexey,
yes.
can I have a question?
Yes.
My question is following. You said that you don't have a necessity to specify the structure of considered Carnot group. But I think that in Euclid space, problem of the finding of such Hausdorff dimension was considered early. And do you have some specific problem related to the fact that you have a Brownian motion, especially in Carnot group, or it does not matter where to consider it? Then why don't consider the Euclidean
this
spaces?
is what I wanted to say next. So about what is known on this topic. Unfortunately, I cannot claim that I find that I know every paper. So if you have some paper suggestion, please. But I think the problem here is that this intersection with something, it actually was very rarely considered. Usually people consider just trajectories, even sometimes, even mostly the trajectories of just one process, not some independent process. Yeah. And here I have independent process and intersection. This is was only considered in rare cases, in particular paper of Legal 188. He considered Brownian motion, standard Brownian motion, and this set was basically so that he considered the set of intersections of these processes. So this was legal, yeah. But his result was not just Hausdorff dimension. He found exact Hausdorff measure of the set. But if, of course, without this, there are a lot of works. For example, started with Czyżewski, Taylor. I believe it's something 62, when they proved that Brownian motion in the dimension D have exact Hausdorff measure with a function R square double logarithm 1 over r. So this is known for Brownian trajectory. And then there was several works for trajectories of different processes. There are a lot of works for Levy processes, I believe, from special type of Levy processes. I saw something about Brownian sheets and so on. And this is all different process from my process, so I do not know if any works related to my process that ask for specifically that. The works about the process that I'm considering was also by Legal, but he only considered again one process and the Hausdorff dimension of its trajectory. Yeah, there are also a lot of works where instead of some fixed interval, there can be some set E. This is also very interesting, but I decided to not include that today. So there are also a lot of works that consider just X from some E, some set. Again, if I skipped something important, please tell me. So as far as I know, this is towards this, in this direction, this is what is known.
But actually, my question was not only about previous studies, but also about the difference. What is the difference between the Euclidean space and Carnot group? Because you said that you study in Carnot group. There is essential difference, or we can forget about Carnot group and just begin to study Brownian motion in Euclid space.
Maybe it is true if the set A is somehow more complicated. For example, even if I take A some manifold in the Euclidean space and then say that this is usual Brownian motion, I'm not sure that it is known. I do not know. Maybe if you tell me, I will look up, but I just I'm not sure 100% that something is known for sure for this, but maybe. There are some works that include this type of estimates. Maybe it's included in the works where this is considered. Maybe I just I think I saw something about thermal capacities. Maybe this can be. I do not remember exact reference, but maybe. Yeah, but this is very good question because this is exactly exactly what is what I wanted to see if I can find something new here. But to me, when I started studying it, the important part is that what kind of Hausdorff dimension is here. So because we can have different Hausdorff measures actually, and in previous talks I presented you these different Hausdorff measures, and we can ask questions with every different Hausdorff measure. For example, in LEGO, in paper of LEGO, not in this one, but the one that studied such processes, because when we have this process of Brownian motions on Carnot groups, on Carnot group we have so-called Carnot-Carateri distance. And if we consider Hausdorff dimension with regard to this distance, we obtain different Hausdorff dimension, maybe. And actually, it was proved by Legal that, well, not dimension, but Hausdorff measure can be different with different rho for such processes, for his processes. For example, for this process, he considered this question. And yeah, so the question here also, what kind of Hausdorff measure do I need to use? So when I combine all that, I do not think it is something known. Maybe the standard Hausdorff dimension, it is in some sense known. I do not, but I still, again, if the process is somehow not standard elliptic, I also am not sure that it's so easy.
Here is maybe the difference because as far as I remember, last year talk we discussed the function for Hausdorff measure, and it seems to me Taylor was the person who studied the intersection points of Brownian motion in the plane with the Hausdorff measure define it with the function containing logarithm. Yeah.
Yeah, but
So
yes, this
this,
is legal. This is paper of legal. Maybe Taylor did also something, but
yes,
legal find the exact.
Taylor did this for sure. And also,
Maybe.
my guess was that this logarithm is related to the potential, which is related to the initial process in the space. So maybe here is the difference between the Euclid space and Carnot group, because the potential in Carnot group has different
Yes, of
asymptotics or
course, it is
functions.
different, but the
Yeah.
problem, what does it mean for me? Of course, yeah, but again, maybe it can be somehow included. I don't know, but
Okay,
mm,
let's go for your results. Yeah.
yeah.
Mhm.
So, oh yeah, I also want to say that if I wanted, if you want the exact Hausdorff measure, then sometimes you need some kind of asymptotics for local time, some kind of double iterated logarithm law or something like that. And in
Mhm.
this regard, I think papers of Chen are very interesting. But for me, it's just one step ahead. I cannot just give you exact something exact today. I will only talk about Hausdorff dimension today, which means I do not give you exact Hausdorff measure. So let's move on. So suppose we have a Carnot group and rho. Well, for me, this is interesting because I need rho to be just a pseudo distance. So this just does satisfy this equation, and that's it. Because I will use it. I will use um, Hausdorff corresponding constructions with such measures. I don't think it's a problem if I use such measure, if I use such pseudo distance. So with this pseudo distance, we can define capacity in the standard way with some power r, and the same here. Power s here means that it is Hausdorff measure. Well, actually, here I'm not. This is not correct. I should say that it is spherical measure. And then that Hausdorff measure is equivalent to spherical measure. And for me, it doesn't matter if it's Hausdorff measure or spherical measure. What is the difference here? I only use this type of sets. And for Hausdorff measure, I should use arbitrary sets with diameters less than corresponding rho e. Yeah. So this is the difference. Less than epsilon, probably. It's correct to say, right? And diameter with regard to this rho, of course. Yeah, for me, it doesn't matter today. So I will consider spherical measures, but I will call them the same as Hausdorff measures. And then we can also introduce Hausdorff dimension, so we can study it. And for me, it is I study the product of Carnot groups. And as you will see, it is important for me to be able to consider such distance in the sense that I want different coordinates, different groups have different weights in some sorts. Yeah, so uh, I'm not just taking maximum as usual for the if we take this Descartes product of metric spaces, then this is just maximum. But I want to add some power here, and this is why I only have pseudo distance because so I could add any power here. In fact, you can also do it in the situation when Li is 0. But because we can just assume that this is 0 if this is less than 1, and infinity if it's greater than 1. And actually, I think it's all works out. If it's not, tell me please, but I think it should work out. In the sense that it doesn't matter. Here, for example, if we consider a ball, and if Li is 0, this is just less than 1, and it's not a problem. Okay, so we can have corresponding capacities, Hausdorff measuring dimensions for this distance, pseudo distances. Yeah, and now I want to have some definitions. So first thing, what I will do is I will tell you something about Hausdorff dimension and measures of smooth manifolds in this in this product of groups with regard to this distance. So for this, I will need so-called codimension. In fact, you will see that it is the name is if I call it codimension, then it is reasonable. You will see it later. But what is this? I just well, this interesting definition because it's hard to explain intuitively. But basically, what happens is I just look at the such directions. This is directions that look outside of this H, outside of the level set of function f. This is these directions, yeah, and then I choose many these directions so that they be linearly independent, so they and they will be not exactly m, so exactly the dimension of this function. So typically, if I do it in Euclidean space, then this is just m vectors and that's it. But here each vector has weight, and its weight it's homogeneous dimension of this corresponding LE in the Carnot group. In the Carnot group, different directions have different degrees, and some directions can well, these degrees are integers. They can be 1, 2, 3, and so on. So they can only be positive integers. But here we have a degree PE. This is degree corresponding to this direction. But then we also multiply it by weight LE, and this is the same weight that I used in definition density of the distance. So this is some kind of weighted codimension. Okay, so we have that, and then yeah, and then this is a technical moment. Unfortunately, the problem is that in the Carnot groups, there are some bad points on these manifolds. These bad points, they're hard to study, so I have to just throw them out for now. So I will consider a so-called set of non-singular points. This is a set of such points that in some neighborhood of these points, we have this type of set of vectors. They will have a fixed rank. And here I will take all the possible these directions, yeah, that are such that they corresponding homogeneous dimension less than something. Still equals at something. So this is just technical condition. This condition, for example, help us with the following. So if this condition holds, so if x is like that, then this codimension will be constant in some neighborhood of the point x. And this is very good. This is actually what I want. So if it's not constant, it can be not constant. Then something bad happens in the neighborhood of this point. So I have to exclude this point. This is technical moment, but it's very important because without it I cannot do anything. So, but if I only consider these points, then it is possible to prove. Unfortunately, the proof involves two theorems from two of my papers, which I do not. One paper is published in 2019, and the other one maybe will be published 2026. It is right now the review. So what does this theorem say? It says that asymptotics of the surface measure of this both with regard to this distance that I define, pseudo distance that I defined, is exactly the t power this fixed power. You can see it's above and below we have the same power, which is important. And it only happens in these points. I can do it. Actually, the upper estimate is in any point, and it can be generalized. It comes from one. But the lower one is much harder, I think, and then it can only happen in these points. And if it's not this point, that it's not true. I can give you examples when this behavior is some rational power, even when it shouldn't be a rational power, in Carnot group, of course. So it's not
C1, C2, they depend on X, yes?
No.
No.
On X, yes. On X, yes. In Y, no. Yeah, X is fixed. In some neighborhood of these points, we can have that.
Okay. I see.
So, and this is actually main result that I need for the following. So now I can claim that, for example, I know the dimension of the small neighborhood of this point X. Yeah, a small part of the surface in the neighborhood of X. This is exactly the dimension. This is the same as in the previous slide. Yeah, so I can just use it. Well, I show you the proof, but it's actually very simple. We just take easiest ways just to cover with non-intersecting balls, and then just give them a higher radius so that they will cover everything. And this is typical construction. And here it just works, I think. And gives one estimate. The other estimate is even more simple. It's just typical. If we have a measure that satisfies this condition, this condition, then it follows that we have this. It's just automatic. Yeah, so this is just trivial. And so we have this exact Hausdorff dimension for the manifolds. But also I need a little bit more. The problem is that when we will consider Brownian motions on Carnot group, then in fact, what we need is this integral, because this integral appears as a condition for the existence of local times. For example, if we take H very specific. So I need the finiteness of these integrals. And this is, on last talk, I gave you even a kind of Hausdorff measure related to this. This is, of course, related to some potential. You can define potential using this, and there is Hausdorff measure, kind of Hausdorff measure related to this. But it appears it is hard to study, so today I will not do it.
Alexey, can I just have a remark that this inequality reflect the idea that now we have a relation to Carnot group. We have a process such that its transition density can be estimated by the distance in such
Yes.
powers. Yeah.
Exactly. So this distance rho I, this is exactly the distance that is related to GI and related to the XI, which is Brownian motion of GI.
Okay.
So this is
my idea is the following: if we have some manifold or Euclid space, and we have diffusion on this manifold, and we have the right estimation related to the distance on the manifold, for example, to the Riemannian distance, yeah, then one can proceed as you did, yeah.
maybe I will reserve this because I may have for now maybe, but maybe I will use something else later, which is not known for some cases.
Okay, good.
But maybe, yeah, for now maybe. And I also need a condition for this to be finite, and the condition is this. And as you can see, the difference is that it has to be true. This has to be true for all lambda. Instead, here I just for one lambda, it was enough for something like this. Yeah, the difference that before. This was related to the integrals, to the integrals with power with this power. Yeah, so it was related to integrals from with gamma, not with rho e. So if I give this integral, then the condition is such that it has to be for all lambda. So for all direction, for all possible this gamma lambda, we have to have this. Okay. yeah, and the proof is basically we just one side we can just use the estimate with gamma lambda, and then just estimate from above as before. And on the other direction, this is a theorem from my paper again, 2018. It turns out that we can here we can transfer this to the some measure nu from some again some balls, and here we need to estimate on balls with different here this ball 1 will be x1 r1, and then times ball 2 x2 r2, and r1 r2 are not connected, they are arbitrary but small. And in this case, it is possible to have an upper estimate also, and it is basically the same. So this is how it done is in the other direction. Okay, so now I will have to skip a lot of things and just tell you that there is a theorem. It is unpublished again. But it basically states that the process intersects the set H some neighborhood of on this manifold if and only if this condition holds, and this has to be neighborhood of this good point X, and then it happens. Just can take small enough neighborhood, and this will be true. And the condition is this. For any non-negative lambda. So basically the condition, if you look here, the condition that if we put hi qi minus 2 here, then this is the condition exactly. Okay. This is just useful to know, because otherwise how do we study the Hausdorff dimension of this if we do not know if it's empty or not? This is the first step. And then the first result, just a second. Yeah, it's okay. The first result is that I have bound from above, from Hausdorff dimension of such thing with fixed L. So for each L, we can say that this is true. Not that this greater than 0 comes from the previous slide, right? So otherwise we wouldn't know if this was positive or not. And yeah, but yeah, so maybe the part of this theorem would be that if this is negative, then this set is empty. But this is the theorem, and then to prove it, I just have to use well, here I use the same, basically the same that I did a year ago in this similar talk, but let me just repeat it. So I need to take some cover of the set H intersect U. So this will be covered with some sets AK. And then I only select those sets AK that actually intersect our trajectory. And then I take expectation and find how much do I get in the end. And you can see that I get exactly what I need. So the power is exactly what it has to be, and we obtain from this we obtain that if we intersect it with this set, then then this will be 0, and then it means that, well, we can just set delta to 0 and obtain our result. Okay. But this is just one side in the one direction. In the other direction, I want to estimate from below, and here I need to study local times. Unfortunately, maybe fortunately, I do not know. But here I need to define local time, and this is lemma. But this is actually also proved in my paper 2019. Well, it's not. It's just partial case of what was proved in 2019 that. Such L exists. It just passed to the limit. We take some approximation pass to the limit in L2, and we find that such L is well defined. I say that it is measure, but actually I can just define L from some set from, well, I only will need this set. Yes, so I only need to define this. So I only need to define some specific local time, and it's yeah, sorry, I will have to also integrate by L. So no, I have to define this random measure, but it is defined the same for all the sets. So here I just need to use results 2019. I will skip that. I do not think there should be any problem, but yes, so I probably need to be more precise here, but with this definition. But I think it's more or less clear that if I have some estimates on of this type, yeah, then I can do this construction. Okay, and then we will have local time for the intersections of these processes on the set U intersect with H. And this will mean that I can prove the following. Here, unfortunately, I will have to, the lower dimension is not the same, is not always the same as the upper dimension. This is some kind of this complicated construction. Maybe it can be simplified. For now, I just decided to leave it as it is. But what's happening here is that we have to, we know that 2 lambda E minus MF lambda X is always positive for all lambda, because this is the condition for intersections to exist. Yeah, for the set to be non-empty. But then we add this minus Ri here. So we replace it with 2 minus Ri, and we make Ri larger until this condition fails. And the moment when it fails, this is our supremum. Of course, we can have different ways to make Ri larger. Yeah, so there are kind of different directions. So maybe for fixed L, yeah. So basically, I cannot say for now what will be the supremum for fixed L, even though this is just a minimum of linear functions. There are finite set of linear functions, and we take minimum of these functions, and this is what's happening here. But in general, if n equal 2, I believe I can prove that this supremum it will be exactly as this dimension from this theorem, but only at one specific L, and that's it. So we will have exact dimension only for one fixed L, and I suspect that something like this is true in general. So this is this lower bound will be equal to the upper bound only for some specific L, and that's it. I do not know why it's happening like this. Maybe I just need to improve my estimates, but maybe the dimension is different. I do not know. Yeah, but what is the proof? The proof, we use local time, and we estimate such expectation, and then we can see that there is this is why rho I. We needed rho I, because here it appears, because here we just estimate densities. We take densities of the process and we estimate them. This is what we get. And then the trick here is that we integrate over a small set, yeah, small ball with regard to distance gamma L, and therefore we can just change it into this slightly smaller, on modulus it is bigger, slightly smaller powers, and obtain some multiplier instead. And this multiplier will be exactly like this. So this will be exactly as here, yeah. Yeah, so this is this is almost the end of the proof. The rest is just a standard argument, because we will have that local time divided by this is basically bounded in some sense, well, almost everywhere or something. Well, it doesn't matter, but you can do it rigorously. And then we will obtain that corresponding Hausdorff measure will be bounded from above, and then we will get this result about dimension. Bounded from below, yeah. So because if we have this, it means that H greater than equals than L. And H corresponds to this order. Okay. Yeah. So more or less, this is what I wanted to tell you today, because for now, this is all I can do. Of course, I was hoping to make some precise estimates, but as you can see, even with dimension, there are some problems with that for now. Maybe I'm using wrong dimension. Maybe, I do not know. Yeah, but this is it.
Okay. Thank you very much. We have a time for questions. Maybe someone have questions or comments, please.
And what is Carnot group? Can you tell us? You have time to explain.
Okay, yeah, I have time. So usually I always prepare slides for Carnot groups, but this is one. Yeah, so I will have to write. Let me just go. No. Okay. Maybe where is this new page button? Yes, just a second. Yeah, here. Okay. Just a second. Yeah, I'm sorry, but some reason it doesn't work.
Alexey, maybe Katerina can raise whiteboard and you can write.
No. I just something is wrong with this, because this is I do not understand what's happening. Just give me a second. This should be easier, but I don't. Yeah, there's some bug here. Maybe I just. Yeah, sorry. Okay, yeah, well, maybe you can create the board, because I have some problems with this program. Doesn't work as I expected to. Even though I
Katerina,
add new pages, it
can
doesn't
you
show the
organize
pages.
whiteboards?
Okay, definitely created some new pages, but apparently it's just the same pages as before. It's just cloned them for some reason.
Okay.
Could you write?
Yes. So what is Carnot group? So we take RD, and we take some kind of operation, group operation. It's a group operation. So that this is Lie group. So this is just Lie group, first of all, but also with the base space RD. Then we consider such numbers P1, PD, so that if we take delta lambda x from some x in this group, and if we take some coordinates, and this coordinate is just multiplied by lambda pi. This is dilations. Lambda just greater than 0. And then we have that these dilations are so that they work like this. So the group operation just does not change the dilations. This is a group automorphism. That's what it's called. And so if we have this, it is easy to prove that the group operation, maybe I need to add some, but I think it's easy to prove that the group operation is polynomial. Then, and additional condition here is that we have to have an analog of Hermander condition. So if we, for each Lie group, we can define the set of vector fields in its Lie algebra. You can just take left invariant Lie algebra, the left invariant vector fields such that they are basis in this set of left invariant vector fields. You can define them. Typical definition is you can differentiate the group operation and then set y equal to 0, and this will be this left invariant vector field. If I hope I did not make a mistake, but I think this is true. So this will be this left invariant vector fields, one of the possible definitions. You can also define them as some basis vector at 0, and then because they left invariant in all other points, the value will be automatically transferred by left invariance. And this will be the same in the case when this is differential by y coordinate. This is the same if actually I think it should be the same. Okay, doesn't matter. But basically, one more condition here is that if we take only vector fields related to the all this p such that p power is 1, so suppose that p1 equals pk equal to 1, and then pk plus 1, and so on. So pi will be greater than 1 if I greater than k. Yeah. So in that situation, we will have that L1, Lk generate all L1x, okay, L1 k, and generate in the sense, okay, maybe I should write more precisely. So if we take iterated commutators of these vectors, m minus 1, LIM. So we take m commutators, and we take ek so that they Eij will be from 1 to k. So only this related to the first k. Yeah? So this generates, if we take a point x, so this dimension should be maximal possible. Yes. So for some n, so there exists m, so that such dimension is maximum of linear span, of course. And this happens for every x. Yeah. So this is basically a Hermander condition for such vector fields L1, Lk. And this is also has to hold. This is just some restriction on the structure, so this group doesn't become a bit strange. Yeah, and these conditions define this group. You can prove, yeah.
Alexey, can I ask you such interesting? You recall this Hermander condition. It was my question too. And you see, we have a lot of diffusions which satisfy Hermander condition, but doesn't have elliptic operator. Yeah? So then, can you say that for any such diffusion with smooth coefficients which satisfy a Hermander condition, one can build some Carnot group for which this diffusion can be a Brownian motion in it, or not? What do you think?
Well, this is, yes, I usually tell about this, but again, so there are known results. There are papers by Hermander, actually, I do not remember the year, and also by this one, the second one, I do not remember. There are also other paper. Basically, what we can do is if we fix a point x, and if we take any diffusion with Hermander condition, then it turns out that in the neighborhood of this point, it can be viewed as some projection of, not viewed as projection, but close to some projection of some diffusion on Carnot group. So there is a Carnot, we can define, maybe not Carnot group, because there are some complications, I believe, maybe with a shift, something happens sometimes, but in general, there are some Carnot group or something similar, something very similar on which we can define this Brownian motion, and then it turns out that we can erase some coordinates from this Brownian motion Carnot group, and what we obtain will be very close to this diffusion. This is a construction that was done, for example, by Hermander to show that this is possible.
So it looks like it is a locally Carnot group, yeah? Locally.
Yeah, well, the approximation was in the sense of operator. So this, of course, not a probabilistic result. He considered operators that correspond to such diffusion. Yes, so and the operators that correspond to such diffusion, they can be approximated by operators that correspond to this Brownian motion Carnot group, but only if we add some coordinates. Yeah, there are some artificial coordinates that have to be added sometimes for diffusion.
Interesting, because in the case of elliptic operator, it was done by Stanislav Molchanov in 1975. I think he said he proved that any diffusion can be treated as Brownian motion on Riemannian manifold. Yeah.
You mean this in this sense? No, what I mean is not exactly as Brownian motion, but something close to Brownian motion. Here, problem is, of course, if we take another point, we can have another completely different Carnot group in theory. So I do not know. So what happens between? I'm not sure.
So can you demonstrate us, at least in case of the Heisenberg group, what will be your estimate? What will be your estimate for concrete manifold?
It is an interesting question. I think yeah, so the thing that I showed you, the codimension, is actually what I told you before, ML, MFL X. Yes, so this is a codimension for the Fx equal to 0 at point X with regard to some L. Well, it is the simplest situation is when n equals to 1, actually, and then we can just work with codimension of this in some Carnot group, this standard codimension. This one I defined before, and I showed you example earlier. So what happens, there are some, if point is not very bad, then it's just some typical, for example, if you want Heisenberg group. So in Heisenberg group, we have L1, 1, 0. For example, this is one of the possible groups. L2 will be not 0. We can just put it 0 here. And then L3 will be 0, 0, 1, something like this. Which means that, for example, if we take x3 equal to 0, I believe, so what happens, we should look at the action of fx equals x3. So action of this vector fields on x3 will be like this. It will be L1f, it will be so it dx1, x2, yeah, and L2 will be 0, and L3 will be 1. So yeah, so as you can see, we can always take L3, but sometimes L1 we cannot take. So if you want minimal possible, here is 1, 1, 2, and we have to select some of them. So to exactly one of them in this case, because this is standard codimension 1. We have to choose one with smaller degree. So we have to choose this one, but not always. Sometimes we have to choose this one. And the points where we have to choose this one, this is bad point. This is exactly singular point that I was talking about. But if we select this, then we have codimension 1. This is it. This is an example. You can make it more complicated. For example, you can find codimensions of some curves, and sometimes it can be different, I believe. Yeah, for curves, sometimes the tangent vector will coincide with one of this L1, L2, and then codimension will be 3. And when it will not coincide with this with linear combination of an L1 and L2, then codimension will be 2, I believe. So for curves, there can be different codimension for sure. And of course, if we take more m greater than 1, then this is more complicated. And I had examples, but not for some weight. For some weight, this weight complicates things even more. So I do not. Maybe it is interesting to find some examples in this direction, but for now I do not have interesting examples. Sorry.
Okay. Thank you very much. Maybe someone else have questions or comments? If not, then thank you again. And for today, we finish our work. Katerina, who will be the next speaker?
The next speaker will be Alexey Bronsky.
Oh, nice. Okay, so for today, that's all. And see you next week. Bye.
Okay, bye. Bye.
Thank you. Bye.
See you. Bye. Bye, everybody.